Hello, this is Dr. John, your physics professor. Today we are looking at another projectile problem. Here we have a rocket that's being launched at 60 degrees to the horizon at 75.0 meters per second. And the rocket accelerates extremely rapidly and reaches this speed very quickly after launch. And then after that does not accelerate anymore. What we want to know, what we're being asked, is how far above the wall does the rocket go? Like by how much does the rocket clear the wall? So to do this question, we're going to divide this into pieces. We're going to do one little piece at a time. I'm going to write the pieces up here and then we'll follow along with them as we go. Here I've written out the three components that we're going to do, the three pieces we're going to do with this problem. The first step we're going to do is divide the velocity. We're given the velocity in this direction at 60 degrees to the horizon. We're going to divide it into components. Then we're going to calculate how long does it take for the x component to reach the wall, because we're dividing up the x components from the y components, looking at them separately because they act independently in a sense. There's no forces acting on the x components once the acceleration is finished. And the reason it says that the acceleration happens really quickly is so that we can basically, at launch here, we can have the initial velocity being this, simplifying the calculation. And then secondly, we're going to calculate how long it takes to get to the wall. Using this x velocity, we want to find out how long it takes for the rocket to get here. Just the x component, that's all we need. Remember, we're looking at them independent. X and y components are independent in these kinds of projectile problems. And then thirdly, we're going to look to see when the rocket hits this wall, in that time, how high is the rocket? Obviously, it's going to go up and down. We don't know if it's still going up or if it's starting to come down or not. We'll do that in that third part of the calculation. So first of all, let's divide this into components. So here I have the initial velocity drawn out here in vector form at angle theta to the horizon, which we know is 60 degrees. And then in red, I've drawn the x component, Vx, and in green, the y component, Vy. What we want to do is we want to find out each of these. Now notice here initially, what we could have done is we could have put this component over here, like this, and then we have this vector plus this vector equals this vector. However, we can always move vectors around as long as we keep their direction and their length the same. And it's a little easier for us to work with it over here. So take a look at this here. If you want to look at the geometry here, this is the angle, theta. And we know from our sine, cosine, and tangent relationships that there's a relationship between the lengths of these sides and the hypotenuse. If you don't remember that, go back and check some of my other videos on the basic definitions of sines and cosines. So what we have here is we have the sine of this angle, the sine of theta is equal to the opposite, that's Vy, over the hypotenuse, that's V0. We can take this, move it to this side, and we're going to have Vy is equal to V0 times sine theta. I'm just going to write that up here, sine theta. And then similarly for the x component, we would have this component over here, which would be equal to V0 cosine theta. I'm going to write that up here in red. That's the very first step, and that's the first step that we do for pretty well all projectile problems, is we'll divide up the initial velocity, or sometimes we're given the final velocity upon impact. We divide it into x and y coordinates so that we can deal with those independently. I'm just going to erase this here, and I'm going to put in the actual numbers for these. So here we have Vy, which is equal to V0, which is 75, the sine of 60 degrees, which is 75 times root 3 over 2, or 64.94 meters per second. Notice here we have three significant figures. Here we have 3. I'm going to keep 4 during my calculation. Usually keep at least 1 more during your calculation so you don't end up with too many rounding errors. And then when you're doing your final problem, your final answer, then write your final answer in there. I'm going to write these answers over here so that we can use them when we need them. There we go. I've written the Vy over there. And now we'll do the same thing by calculating the Vx. So Vx is equal to, right over here, V0 cosine theta. This one is 75. And we want cosine of 60. Cosine of 60 is 1/2. So this times 1/2. I calculated it to be 37.5. I'm going to write that down here so that we have that for later as well. I've written Vx down here. We already had Vy up here. Now we've done that first part, dividing it, the initial velocity into components. And secondly, let's calculate how long it takes for the rocket to get to the wall. So for that, we do not need the y component, we only need the x component, because the x component, which has no forces affecting it, will determine how long it takes here to get to the wall. We have a distance that we need to travel, 27 meters. We have a velocity in the x direction, 37.5. If you need help remembering this, the way that I do it is velocity is equal to distance over time, meters per second, but I want the time, so I'll take the time over here and divide by the velocity, and I'm going to get time, moving that over there, equals d over v. If you want to check the units, this is meters per second. You flip and multiply, you're going to have seconds on the top, so this is correct. So we'll want d divided by v, just like this. We want 27 divided by 37.5. I'm getting the time to be 0.72, the time it takes to hit the wall here. I'm going to write that down right here. Time to the wall is 0.72 seconds. It's a little bit small there, hopefully that you can still read that. So now we have found out how long it takes for this rocket to get to the wall. How do we calculate how high it is? Well, we have a bunch of equations that we can use, and what we do is we look through the different equations, see which ones might be useful for us. So one equation that we have is that the height that it would be after a certain time would be the initial height plus the initial y velocity. I won't put the initial velocity, I'm going to put the y velocity times time plus 1/2 acceleration times time squared. So this is an equation for any distance. The distance is the initial distance plus the velocity in that direction times time plus 1/2 acceleration times time squared. As we use this equation, we're going to have to be careful of what's positive and what's negative. Of course, since we're starting on the ground level, the initial height is 0. We don't need to worry about that. We can drop that element altogether. I'm just going to erase that so that we don't have too many things up there. The initial velocity is going to be the y component. We're going to look at upwards as being positive. So the height, the y height, is going to be the initial y velocity, which we have right here, 64.94, upward, times the time to hit the wall, 0.72, plus 1/2 acceleration. But acceleration, remember, we're taking the velocity as upward, acceleration is downward. So we're going to have to make this a negative acceleration. I'm just going to put a negative sign in there to make that easier, so I don't have to put a negative in the bracket here. But what's the acceleration? 9.8 meters per second squared. Acceleration of gravity, we multiply by time, 0.72 squared. So here we're going to have a couple of components. We're going to have this first component and the second component. Here I've multiplied out this here, which is the component of height determined by the initial velocity, 46.76. And here's the reduction in height determined by the acceleration of gravity. So notice it's going to be pretty high already, reduced only slightly by gravity. Subtract those two to get the total height, and I'm getting 44.22. 44.22 meters. So that's how high it's going to be. That's not the final calculation yet. We have one more thing to take care of, and that's the fact that the wall is actually 11 meters high. So since the wall is 11 meters high, we're going to have to take this calculation and because we want the height above the wall, reduce this by 11 meters. I'll erase some of this and write the answers up here. So here we have the height that it went to, 44.22. And we want to subtract 11 from that. We're going to get 34.22 meters. Now, of course, we have to check one more thing before we put the final answer down. 3 significant figures, 3 and 3. This has 4. We want to take this to 3, so it's going to be 34.2 meters. That's with the correct significant figures written in. So there would be your answer as you'd write it out. This is the amount. And when I write out an answer like this to a word problem, if this is a word problem, I would write out the rocket is 34.2 meters above the wall. That way you've clarified that it's above the wall. In case you accidentally wrote it's 44.22 meters above the ground and you've forgotten about the wall here, which is one more little step, you'll still get partial marks probably for that. But this is the actual answer they're looking for. If that helped, like and subscribe and continue to check out more videos. I'll see you later. Bye-bye.